Okay, do we have any questions before we get going today? Who here, did anyone here now go to the programming competition thing last night? No? Must have been the other section then. Okay, last time, if I remember correctly, we were talking about tests, right? Yeah. And how far did we get? Did we get to the broken example? All right, well, someone said yes, someone said no, so we'll go here. This is what we're going to do. We're going to use the assert keyword. The assert keyword will do nothing if the statement next to the assert is true. If 5 equals the absolute value of 5, if that is true, assert will do nothing. But if the expression evaluates to false, then the program will fail. Now this is an example of writing tests for the absolute value function, which we do not need to test because it's given to us and we can assume it's correct, and if it's not our fault. But there we go. I hit run, and this produces no output, but that's good. That's a good thing. Nothing's wrong. If, for example, I wrote a test that's wrong. Now, to be clear, this is going to crash because that second test is going to fail. But the test is going to fail because it's a bad test, not because there's anything wrong with the absolute value. I'm checking if the result of absolute value of -5 is equal to 6, which is of course not going to be correct, so it crashes. It says assertion, and it even tells me which one, the one on line 2. And then I look at that and go, oh, I just wrote a bad test, great. And everything's fine. Now showing you an example of doing that with the absolute value function is a little silly because it should work. But here's an example of doing it on a function I wrote. Now, what I wanted to do was write the absolute value function. And ignoring the fact that I need this broken absolute value, let's pretend it should be correct. If this is correct, I know what the test should be. I don't even need to write the code before knowing what the input and output should be for that function. If the absolute value function is working correctly, I know what the input and output should be without even looking at the code. I don't even need to start writing the code for the function. I can write tests for a function that I'm going to write before I write that function, if I know what that function is going to do. If I don't, well then why am I writing a function if I don't know what I want it to do? So here we go, but this one's going to fail because there is something wrong with the function I wrote. There's an error, there's a bug. And this is a good thing. We want the program to crash if there's a problem with our function. It's better if the program crashes and kind of gives us a point in the right direction of where it failed. It's better if it fails than it runs with some mistake that keeps getting compounded and changing throughout the rest of the code. Next thing you know, the earth blows up. It's better for it to not run if there's a problem than for it to run with this problem silently. Now, that's a really contrived example, but let's look at this example right here. This is the square of some function that we wrote in the function topic. I'm going to hit run and everything's fine. First and foremost, you'll see, well, there's a good doc string there. Of course, we like to write our doc strings to describe what the functions are going to do, no matter how simple it is. And then I describe the parameters, I describe what it's going to return, there we go. But I could ignore all this code. I could imagine I didn't write that code and I want to write that function. And I know what I want the function to be called. And I know what I want the function to do. If I know what square of sum is going to do, I know that the square of sum of 0, 0 should give me 0. I know the square of sum of 1 and -1 should give me 0. I know the square of sum 5 and 5 should give me 100. I know this because 5 plus 5 is 10. 10 squared is 100. So if the answer was right, if the function is correct, when I give this function a 5 and a 5, I should get back 100. If I don't, there's a problem with the function. Similarly with -5 and -5. And I'll talk about this in a moment. Comparing floating point values is tricky, so we have to use a little bit of a trick. You compare the absolute differences, but we'll get there in a moment. You'll notice when writing tests for the code, we want to be thorough. And we want to check various cases. If I go back to the absolute value example, there's a reason I picked a test, these three values. Can anyone take a wild guess why I picked those three values for my tests? Take a wild guess. What do you think?
Because you know the answer.
Well, true. That is one reason I did it. But what else?
Because there's a positive, negative, and a zero.
Exactly. I wanted to test a positive number, I wanted to test a negative number. It didn't really matter which positive or which negative. And I wanted to test zero, because zero is kind of a funny one, right? Zero doesn't have a sign. So let's just check zero. So the decision of what I was testing played into, I want to gather the different scenarios of how this function could be used. No sense testing two of the three ways the function could be used, because what if the third way it would break? If you never tested it, then, well, you screwed up. So here I'm testing zeros, a positive, a negative, two positive, two negatives. Maybe I should have checked a negative and a positive as opposed to a positive and a negative as well. Maybe there's more cases I should have. I could have missed some, but this is probably pretty good. Now, there are a lot of things I could have tested, but there's no sense, like if I test two positives, if I test 5 and 5 and it works, I have no reason to believe it wouldn't work for 6 and 6, right? Maybe it doesn't, but, you know, kind of like deciding which things to test. You know, you be intelligent, be as thorough as you can, but don't go crazy. Now, this whole thing here, if I actually wrote sum of square 2.2, 2.2, Python will give me back 19.36000000000002 or something ridiculous. Because computers suck with decimals. Who here remember me explaining why? Two people, well, I'll explain it again in a moment. They suck with decimals. They really do. And if I try to compare 19.36 to 19.36000002, it's going to say, no, those aren't the same. But the function was correct. This is an issue of the computer. So the trick in this situation is to take the absolute difference between what you want to compare. Right? So I want to compare the square of sum 2.2, 2.2, which I'm expecting to be 19.36. And if the difference is small enough, I'm happy. That's the trick. So even though they're not equal, if they're so close, we're fine with it as floating point numbers. Now, how close should it be? Kind of depends on the situation. If I'm writing some code to calculate the distance from my house to work, in kilometers, 0.001 is probably fine. If I'm calculating something for the space station, maybe 0.001 isn't good enough. I should maybe get a little bit more precise in my test. I don't know. But it depends on the situation. That's up to you. If the difference between what I get and what I want it to be is 0, obviously they're the same. But if they're close to 0, knowing that floating point numbers are funny, I'll call it a day. I'll be happy with that. Now the reason computers suck with floating point numbers really comes down to that whole issue of infinity. Everyone, you better help me out here. This is a big question. It's a tough one. If you can't get it, you need to reevaluate your life. What comes after 1? 2. Good, very good. One person passed that test. See if you can pass this next test, everybody. What comes after 2? Hey, more people. What comes after 7? What comes after 1,000,000? You You're doing very well, everybody. So now I'm going to modify this question a little bit. Okay? And if you get this wrong, you better quit right now. Those were integers. Let's go to real numbers. Real numbers meaning decimals. You have decimals. What comes after 1? 1.1? Does 1.1 come after 1? Oh, yeah, but you also skipped a few. What about 1.01? What about 1.00? What about 1.0000001? We've got an issue here. Exactly. So, where with integers, I can keep counting towards infinity. But the point is, I can put my finger on each number as I go. I mean, these floating point numbers have that same issue. The real numbers have that same issue. I can just keep going bigger and bigger and bigger. But we also have this funny issue of like, well, there's also like an infinity number of numbers between 0 and 1. As well as all the way up to. This is kind of funny. And the point is, there's actually different types of infinity. And this is what we call like uncountably infinite. And it's actually, like, they're both infinity, but one is definitely bigger. Oh, right? Like, there's more floating point numbers, more real numbers than integers, right? It feels that way, at least. So, your computer, traditionally speaking, you have a 64-bit computer. Your computer can only represent so many unique integers. Now, modern computers and programming languages, we have tricks to do more. But the reality is, your computer's happy with some finite number of integers. Someone's got some beautiful music playing. So, if we have a finite number of integers, but we also have a finite amount of space to store these floating point numbers in our computer, and there's more of them, we're going to have issues here. Long story short, to summarize everything, the programming and engineering world of the computers goes, the floating point numbers, they go like, good enough. That's what they do. And then we deal with it by checking if the difference is close enough. Long story short. This is related to the same issue. Raise your hand if you've taken or are currently taking like first year statistics. One person, two people. So, for you two, you can give me an answer. You can give me a very precise answer. There is a correct answer to this question. What is the probability of it raining 1 millimeter today? 0. Absolutely 0. And you say, well, how do you know? Maybe it is supposed to rain a little later. How do you know it's not exactly 0? Because it's not 0, or sorry, 1 millimeter. It's not, it didn't rain 1.1 millimeter? Or 0.9 millimeter? Or what about 0.99 millimeters? Maybe raise it a little bit. The point is, as you get more and more precise, it's not possible to get like that exact value because you can get more and more precise. You can play that game forever. So that's why in like statistics and probability, you integrate the area of the curve for a specific range. Which is the same thing as just adding up all the values. It's just you have a continuous space. It's a related problem. We only have so much space to store numbers. We can only store so many unique numbers. Floating point numbers, we're going to lose some accuracy there. We deal with it. The benefit of writing tests, first and foremost, if I can write the test before I even write the function. And if I do that, it means I've taken some time to be really thoughtful and deliberate about how my function is supposed to work. So there's value there. It also ensures that my function is correct. Every time I hit run, if those tests are there, if it doesn't crash, I know that it's probably correct. There's no way to really prove that it's correct, but with a bunch of tests, you can be pretty darn certain it's correct. And on top of it, if the code ever changes, those tests are still valid, right? If someone else takes your code and they're modifying something somewhere else in your code and they accidentally add something to this function by accident, and they hit run, suddenly it's going to fail. And it's like, well, why did that test fail? Nothing should have changed in that function. Why did it fail? Some went wrong somewhere. Let's go look. And it says, okay, there's an issue there. Well, why would that be wrong? And then I look and go, who the hell did this? Come on, get out of there. So you write the test once, and then no matter how many times you run the function or you change it a little bit in terms of how it functions, assuming it has the same ultimate functionality, the test will still be relevant. This is fantastic. We know our code's correct, because remember, it's your job to write the code, and it's your job to demonstrate to me that it's correct. You don't give me code and say, is this right? You're learning, obviously you'll do stuff like that. But like if you're writing code, you don't go to someone else and be like, here, I wrote this code, is it right? They'll go, screw off, you tell me. You wrote it. It's not my job to tell you if it's right. You write it, you test it. You show me it's correct. You're not done writing your function if you didn't write your tests. You gotta write your tests. Knowing how and when and which cases to cover when you're writing your tests comes with experience. The first time you start writing tests, you might suck at it. That's normal. You'll just get better as you go. It's kind of a bit of an art form to know when and how and what to test. But start now to get that practice in and you'll become experts in no time. Test your functions. It's not about writing code, it's about writing correct code, and your tests help demonstrate to me that it's correct, me or anyone else. And that's a good thing, right? You don't want people writing code that's untested. Right? Imagine writing, who's going to get in an airplane if that code was never tested? Obviously that's a ridiculous idea. No, test your code. You want to write code? You test it. You do. This is what's awesome about this course. You can work, who here has looked at assignment 1? And you'll see there's a bunch of assert tests under each function I use. I wrote the tests for you. Meaning if you write the function, and you hit run and those tests pass, chances are you're probably correct. Now you can cheese the tests in a way where it'll seem like it passes, but like, if you write the function earnestly and it passes all those tests, you should be pretty certain you're correct. You can know if your assignment is correct before anyone looks at it to mark it. All you have to do is run it and test it. You don't get this luxury in many disciplines. In math, which is probably the closest discipline, you go do it and then you hit it, like, oh, I'm right. Here, you hit run. Did it do what it was supposed to do? Did all the tests pass? Yeah? You're probably right. You probably got perfect or near perfect at least. So this is an awesome thing. If you ever think for a second these tests are annoying, no, they are doing you the biggest favor in the world. They're letting you know if you're right or not. It's amazing. You're lucky. Someone's got to get you some water. Holy moly. Right. Yeah. And that's the example of the floating point numbers, blah, 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 blah. Okay. The above examples that I showed you did a pretty good job at catching various cases, but you might wonder why I didn't do other things like, well, if you tested 5 and 5, why not 5 and 6, right? Sure, they were both positive, but they were both the same number. Should you have tested 2 positive numbers that aren't the same number? And maybe that's a reasonable thing to do, but based on how that function should work, I have no reason to believe that would break it. So it's probably fine, but yeah, maybe I should have added that test. Why didn't I test when the first argument was negative and the second was positive? I tested when the first one was positive and the second was negative. Why didn't I do that? You're right, you're not wrong, but I probably caught it with the other cases. Really, what to include and what not to include is more of an art than a science. Now here's an example of tests for Celsius to Fahrenheit. if it actually, no, it did not. So there we go. Of course, I've got my doc string in there. I'm in great shape because of course I'm doing good. And then I've got the tests. Assert that 32 is equal to whatever Celsius 0 is. Celsius Fahrenheit 0. Again, I could have written all these tests before this code was ever written. Because this should be correct if the function I am about to write, pretending I haven't written it yet, if the function I'm about to write is correct, that'll be true, that'll be true, that'll be true, that'll be true, and these will also be true. So there we go, awesome. Even more tests. Hit run. Remember, if everything was good, you won't see anything. It's only when there's an issue will you see something. And tests can fail for two reasons. One, there's something wrong with your code. There's something wrong with the function you wrote. There is a bug. Or two, maybe your test was wrong. In that, if I accidentally typed, well, 0 is 33. Like maybe I typed it wrong. So just make sure your tests are correct. But those are the two ways. And remember too, the way assert is going to work is not by checking, oh, 32 equals Celsius to Fahrenheit 0. The assert doesn't care about that whole statement. It cares about what that statement evaluates to. So the statement on the right, next to the assert, will either evaluate to true or false, right? So if it evaluates to true, assert true, and it carries on. Only when it's false will it break. Any question about these tests? So, to be clear, just give me 1 second here. To be clear, these tests are great, and they're doing exactly what they need to do. Realistically, if I were to go and write tests like this for software, I would do it a little bit differently. I would use this like a built-in tools and whatnot to automatically do all this testing. But all of that automation is just going to be doing effectively that. All right? It's just in order to do all that automation stuff, we've got to learn a little bit more before we can do it. And we will talk about it later in course, about the unit testing. But for now, this is not only sufficient, it's ultimately the same thing. It's just we've got less bells and whistles. So this testing is fantastic. And yeah, you had a question?
On the first line of the spell, far right, what is the float there?
Right here?
Yeah.
In this one as well?
No, just the one far right.
Well, I'm glad you asked, because we talk about it in like 2 seconds. Just give me a second. Good observation. I snuck that in to see if anyone would notice, and you noticed. All right, Automated testing. Okay, I actually already said that. So we are right there. Type hints. Okay, so in some other programming languages, every time you make a variable or a parameter, you have to be very explicit about what the type of value is going to be stored in that parameter. If I want, in Python, I can say a equals 5, right? Create a variable a, put the integer 5 in it. But if this was something like Java, I would have to say int a equals 5. It's the integer value, it's an integer type variable a, and it's storing an integer. And this is actually, you might find that annoying, but it's actually a really good thing. Because it guarantees all of your code is typed correct before it even runs. That'll become clear as we learn more and more and more. But Python does a really good job of figuring out types for us. However, it can only do so much, and at the end of the day, it's going to follow the code that you wrote. No matter what, it's doing what you tell it. But unfortunately, it's not too uncommon to mix up your types. I have a function that's expecting to take 2 integers, but I gave it 2 strings. Python will be happy with it, but a language like Java, before you ever hit run, Java will say, no, you've got a typo here. Well, like underline and completely red, being like, you've got an issue here. This function takes integers, but you gave it strings. Before you even hit run, which is great. Python doesn't do that. But Python provides a way to not show you that there's an issue. Like, it'll run if you mix up your types. But it has a nice way to be a little bit, at least a little bit more explicit about the types of things. And this is where that float thing comes that you were talking about. This is what we call type hints. Consider this code, right? And I know I've shown you this example before, but here's some code. Calculate and return the sum of 2 provided numbers. First number, second number, the sum of the 2 numbers. And I hit run. And I say, well, I want 1 and 1. And I get back 11, because 1 plus 1 is 11. Right? We all know that. Now, we've seen this issue before. It's because I was thinking this function was going to get integers, but I didn't give it integers. I gave it strings. This would be an example of a situation where Java or C++ or C# wouldn't even let me hit the run button. It wouldn't even have run the program because I would have said, you've got a mixed match of types. Python was like, yeah, cool, do what you want. But that, if you don't catch that mistake, suddenly that could compound into who the hell knows what catastrophic issue in other parts of your code. That's a big problem. Now, the worst part of this too is I could have written all the assert tests for this function, because the assert tests would look something like this. 0 equals, what did I call it? Add together. 0, 0. 1, negative 1, 1, 1, nope, 2, negative 1, 1, and we'll do one more. Let's do negative 1, negative 1. What did I do wrong? Oh no. You didn't even correct me before I copied that how many times? Sheesh. Add to get. There. Look, all the assert tests pass. It didn't crash. So great, the function must be right. But the issue here wasn't with the function. It was with how me, the programmer, used the function. That was my fault. And no matter what you do as a programmer, at the end of the day, you can test all your code all you want, make sure it's correct. But some asshole's going to come along and use it wrong, because it's always going to happen. And this would be an example of using it wrong. But this is such a common mistake to make. And Python will silently crush your dreams if you really needed that to be too. And if it's not clear, the issue is, it's because this function returned or got 2 strings. And when you add strings, you concatenate them. But clearly this was expecting it to take 2 integers. So a way to kind of protect against this is type hints. What you do is you go to your parameters. And don't worry, I'm not going to expect you to memorize the syntax. If you're in the lab today, Monday, Tuesday, you're not going to remember the syntax. You're going to go, what was the order again? Just look it up again. That's what I always do. What you do is you go next to the parameter and you say you're going to be a float. Now, typically, if you've got a function that's going to work with numbers, integers or float, you just say float, the more general one. And it's going to take a float. And then there's this one. This says the variable b, or the parameter b, should be a float. A should be a float. What do you think this means? Someone want to take a wild guess? it returns a float. The arrow type is, well, what is this function giving me back? To be clear though, let me show you here. If I now go write this, like check this out. Add together. Look. First of all, look. Look. It actually popped up the little doc string I wrote. Just look at that. Isn't that cool? I'm using the function add together. And now it's giving me the doc string. And it's saying, hey, the first number. And it's telling me, oh, that should be a float. It's telling me, the programmer, this function is expecting a float. So I know, oh, that's great. To emphasize, if I do this, no, print. Look, I did print and this came with a little pop-up and it's describing what print is. That's print's doc string. That's one of the reasons you write the doc strings with that format, because it describes how to use the function and you get that extra neat little like pop-up, hey, this is what this function does. So now, this tells the programmer using it, it's supposed to be a float. It makes your code a little bit more clear. It makes it a little bit more explicit. But be warned, Python won't enforce this at all. It'll still let you make this mistake. This helps protect against the mistake, but it won't save you. I can still run this with 1 and 1 and get back 11, even though I added the type hints. The type hints are there for the programmer to hope that they don't mess up or make that mistake. You've got no guarantee that they won't mess it up. So from now on, all the code you write, if it's a function, 1, you write your doc strings. 2, you write your assert tests. And 3, you add your type hints. Always do that. It makes your code clearer. It protects it from being wrong. Whether you wrote the code wrong or someone's using your code wrong, this is the better way to do this. Yeah. Now the parameter list, each parameter, it's its type. You can if you want. No, I don't show it here. Yeah. You can even specify in your doc string. You can specify like R type. You could do that there as well, just as an FYI. But yeah, any questions about those doc strings? Or not doc strings, type hints? Yeah.
How would you input float?
How would I do that? Well, I would just convert X and Y to a float. This is how I would do it correctly. It's not the function's responsibility to convert what it gets to a float. The function is expecting it to be a float. This is where kind of where the responsibility would lie. If I wrote the function, it's not my responsibility to ensure that, to verify. If you're using my function, it's your responsibility to read the documentation and use it correctly. I'll do what I can. I'm going to do things like give you type hints, have a well-written doc string and whatnot. But at the end of the day, if you're using that function, you better understand what it's doing. So now it works. And just to make it clear, I'll change these to ints. Even though the doc string, or sorry, the type hints were float, float, and float, clearly this returned an integer, not a float. If it was a float, it would say 2.0. So what you get, whenever they read the description of your function, it tells them what it should be. In Colab, and a lot of other IDEs, you'll get a pop-up with the doc string along with the details of what you're currently looking to add as the argument for which parameter and what its type should be. Pretty handy stuff. What you don't get, Python will not stop the code from being used wrong. The type hints do not enforce that the types are what they should be. It's just there for more self-documenting code. That's really all you get. But that's still a good thing. So yeah, even though the type hints are there, the person can still blow it. Any questions about the testing or the type hints? No, everyone's good? Wonderful. All right. So, here's an activity using only what we've learned so far. Write a function called smush. It takes a number and it checks if the number is positive or negative. If a number is positive, the function will return half the value of a number. And if it's not positive, just return the number. So if I give you 4, it should give me back 2. If I gave you -4, it should give me back -4. Write that function. Take a moment and do that. I'll give you a few minutes to do it. Bless you. Anyone get it working? How'd you do it? Oh, whoa, 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 you broke the rule. You cheated. I said only using what we have learned so far. What are you talking about? What is this if nonsense you're talking about? You did it or you cheated too?
I guess I cheated too.
No cheating. You should know how I feel about cheating. Did anyone do it without using this if statement nonsense? I'll give you a minute more to think about it. Alright, well, I sent you on a wild goose chase, didn't I? Did anyone get it? Yeah, I didn't think so. Yeah, but did you cheat? See, I'm guessing so. Right now, we have no way to make a decision in our code. There is no ability to make a choice on what to do in a situation. We don't have that yet. There's no way to do it. Meaning, I have no way to be like, well, if it's even, do, or if it's greater than 0, do one thing. If it's less than 0, do another thing. I have no way to make that decision. Fortunately, there's an easy way that a couple of people have spoiled the surprise of. But there is a way to do it. We can do it with conditionals. We can set conditions in our code that are going to be based on Booleans. But effectively, it's exactly how you do things with English. If it's greater than 0, return the number divided by 2. Otherwise, return the value. So instead of otherwise, we use the word else. Okay. Conditional expressions. Booleans were already discussed. We talked about that last topic. We discussed them as a type. We told them what they are, how to use Boolean operators, and we showed you comparison operators. So Boolean is a type. It can only have 2 values, true, false. There's Boolean operators, the ones that take 2 Booleans and give you back a Boolean, things like and or. And then there's the comparison operators, ones that might do some comparison on some other things, but give you back a Boolean, like is 7 greater than 11? False. Right? But Booleans allow us to do a lot more than just evaluate an expression to true or false. I mean, really at the end of the day, the Boolean is just true or false. But we can use statements inside our code that make use of these values to make decisions. Consider smush from above. I could do this. We know how to ask if a number is positive. Check if the number is greater than 0. Right? If it is, it's positive. The key is how to tell Python to do what in what situation. So here we go. Here's smush. It takes a float, returns a float. And I say smush of 4, print smush of -4. 2 and -4. Now, one big thing I want to say that I have said before, but it probably didn't stick because there was no reason for it to stick. There's no example of the alternative. Your function will only ever execute a single return statement. It can have multiple return statements. Look at that function. How many returns are there? Oh wait, no. Ah, shoot, I spoiled it. I'll come back to this in a moment. I actually did it a better way here. Here. Return value is a number. Ignore what I said, in other words. I'll hit that not today, next time. The return value starts at a number. And then I check, well, is a number greater than 0? A number greater than 0 will be true when a number is bigger than 0 meaning it's positive, right? So if that statement is true, mind the indent, and mind the colon on the previous line. Mind the indent. Everything indented under that if is what you do if that condition is true. There's only one line here. And then when you're done, you unindent to carry on. So, return value a number. It checks if it's greater than 0. If it is, return value will be equal to return value divided by 2. Then, no matter what, return the return value. So let's follow this code, and we'll see there's a branching that's going to occur. But let's follow this code with this example with the code I wrote. The first time I do it, I'm running it with 4. So I jump up, okay, line 1, yada, yada, yada. Line 10. Return value gets the value what? 4. Everybody wake up. Return value is assigned what value? 4. That was pitiful. Come on, the faster we finish this, we might even leave a minute early. I know, right? Get it together. Wait, what time is it? A minute early. Oh, shoot. Return value gets what?
4.
Hey! Is a number greater than 0?
Yes.
Who said yes? Get the F out of here. Is a number greater than 0? True. Much better. Because it is, we go inside. Return value divided by 2. What's 4 divided by 2? So what value is return value going to assign? 2. We finish. We hit line 13. What do we return? Now let's run the next one. Negative 4. Okay, return value is assigned what value?
Negative 4.
Negative 4. If negative is a number greater than 0. So we skip that chunk of code entirely, all one line of it. And then we jump down to line 13 and return what value? Look at that, you're experts. Great. All right, have a great weekend unless I see you later. Then I know you're going to have a wonderful weekend. Remember, if you're stuck, if you need questions on it or you have anything, be sure to come to office hours. I get lonely.